All right, so using RNNs, right? Having said all of this, we train RNNs on sequences, right? And as a note, we reset their state at the beginning of each sequence, right? So if you have a network that you're training on an image, right, then you might show it one image at a time, right? RNNs are not like that. RNNs are trained on sequences. So an example might be stereo sound, okay? So to train an RNN on stereo sound, and I should say, actually, if you don't know, right, stereo sound consists of 2 channels, right? And each sample, if you're doing PCM encoding, blah, 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 let's not worry about that right now, each sample has some numeric value, right? And if you wanted to train an RNN on sound, you would show it these 2 first, and then these 2, and then these 2, and then these 2, right? So you would run down the sequence showing it 1, 2, 3, 4, 5, right? Okay? Every time you start a sequence, so if you're going to train it on sound, for example, you might have, let's just say hundreds or thousands of samples of people reading from a book, right? If you want to chop that into every word, you would need to reset that state that it carries at the beginning of every word, right? So every word would constitute a new sequence, and you would reset your carried state every time, right? You might have one output for the whole sequence, or you might have one output for each time step, right? So you might have one output for the whole sequence if you want the network at the end to tell you, let's just say, which of, I don't know how many there are, let's say 60 phonemes it is, right? Phoneme being like one of the fundamental sounds that compose like human speech, right? So it's not exactly, I probably shouldn't say anything, I don't know linguistics really, but it's not the same as a letter because different languages use different sounds, right? Like there are phonemes in Chinese, say, that are not in English, or there are phonemes in German that aren't in English. But you might have a set of 60 phonemes, and you might want it to map, right, which of those phonemes appear in the word that was being read, right? Then you have one output at the end, right, where it's got, a 1, for example, in phonemes that were used and 0 elsewhere. Or you might want it to have one output for every time step. So if you were going to do that, you might assign a vector like this to every time step and then attempt to train it to be 1, right, when it thinks that phoneme is being said and 0 otherwise. You could do these things either way, okay? If you're doing text generation, you're probably going to have a target for every time step, right? So I know I mention that right now because a few of you want to do text generation for your projects. If you're doing text gen, you might do that, for example, by training the network to predict the next letter or next word given the letters or words it's already seen. And in that case, you would have, right, so each letter or each word would be the inputs, right? You'd have letter, 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 or word, 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 and then a vector predicting the next letter or next word at every time step would be the output, okay? If we have one output for the whole sequence, right, we evaluate the remaining layers only when the RNN gets to the end, okay? So if we have our RNN layer and our following layer, at least in TensorFlow, right, we feed all of the data set into the RNN layer, and then only after it has seen the last one do we evaluate the following layers on only the last output, okay? However, in TensorFlow, if we are training on a sequence and we have one label for every element in the sequence, then we go through the entire thing every time, right? So if you have one label for the entire sequence, you run the RNN completely, and only then do you call the remaining layers. If you have one label for every step of the sequence, you run the whole network every time. So to train RNNs, we unroll them in time, okay? So that's a little nebulous. This picture I took from Wikipedia. There are many, many variants of this picture across many different RNN explainers. What we essentially mean is we take our one recurrent network, and to train it, we unroll it, right? We treat each use of the RNN as though it's a layer, and we wire them up in sequence, right? So what we kind of do is we've got, if you imagine it this way, right? We take that recurrent connection and we sort of explode it as if it's many, many, many layers, right? Where each layer is getting the previous layer's state, but also the input. That's off the edge of the screen. Could have positioned this picture better, right? And we also interpret these layers as sharing weights, because they are all the same layer, right? We are taking the same single unit and sort of expanding it in time, right? So effectively, we treat our one RNN layer like a very deep network. Very, right? If our sequence is 2,000 elements long, we wind up expanding our one layer into this 2,000 element sequence, right? H of 0, H of 1, H of 2, out through H 2000, right? And that is a lot, right? As you might guess, we get hit hard by the vanishing and exploding gradient problems, right? The vanishing gradient problem might be obvious. The exploding gradient problem we didn't talk about a lot, right? So the backprop error depends exponentially on the size of the weights because the weights are shared, right? Because the weights are shared, if one of the weights gets bigger than one, right? And if we have 2,000, like if we are unrolling to a 2,000 element sequence, right? Then we multiply by that thing that is bigger than 1 2,000 times, right? That causes our gradient, right, our backpropagated error, to explode, to become huge. And unlike the vanishing gradient problem, this problem might actually be much worse with a ReLU-style unit, exactly because they don't saturate in the positive half, right? Which means that a big number like 4 doesn't get squashed. It just keeps getting passed back as 4 times greater than 1 times 4 times greater than 1, and boom, right? So we have the normal vanishing gradient problem because we have logically 1,000, 2,000, however many layers. We also have the exploding gradient problem if one of our weights gets large or one of our units is large, one of our activations is large. So our network struggles to capture long-range dependencies. Vanilla RNNs really, really struggle with long sequences that have long-range dependencies because of the vanishing and exploding gradients problems, okay? That is a problem we're going to come back to later. So, also, computing this requires us to store this entire history, right? If we have our 2,000 length sequence, if we have 40 nodes, right, and on that hidden layer, it requires us to keep all 20,000 of those 40 node activations. For some very large, complicated networks, that can be very, very prohibitive to do, right? So this, if we did the math on it, probably wouldn't be that large a number in terms of like megabytes, but, many cutting-edge networks use layers of thousands, right, of hidden units, use sequences much longer than 2,000, use many more than one layer of RNNs, and having to store all of that could get, wildly, impractically expensive, right? So in practice, with a vanilla RNN, you often truncate the history. You keep only, say, the last 100. But there's a huge obvious problem there, which is that also limits how far back you can go, right? If you're only keeping 100 units, then you better be able, or if you're only keeping 100 states, right, in this huge state history, you better be able to find some useful learning rules in only that last 100 states. Otherwise, you will not train, right? And this, besides the vanishing and exploding gradients, is the third major reason that vanilla RNNs struggle with long-range dependencies, right? If the stimulus, so an event the network needs to respond to, is more than 100 units separated from the output it needs to demonstrate, right? So if the network needs to remember, oh, I saw input whatever 500 steps ago, but you truncate your history to 100 units, you provably will never train, right? So this is another reason that vanilla RNNs don't do great with huge, distant sequences. And yeah, we're going to end up seeing that LSTMs can. All right, slide break.